video is a continuation of rotational kinetic energy with an emphasis on the quantitative approach to analyzing the energy and the speed of a rolling object as it goes down a hill. So if you haven't watched the first video on rotational kinetic energy, I do recommend that you pause and do that. So we're going to derive an expression for the speed of the center of mass of a hoop, or really any object, and then I'll plug in for the moment of inertia of a hoop when it reaches the bottom of the ramp. So a couple key phrases here. Derive an expression is a term that the College Board uses, and really a lot of physics teaching institutions use. That means you should start from a big idea to derive this expression. So you can't just write the expression if you memorized it, but you need to start from a big idea. And the big ideas in the AP Physics 1 course generally follow the units of study. So we've got kinematics or motion, so those big ideas would be some of those kinematics equations. We've got forces, big ideas there being the sum of the forces equals ma, or the net force causes a mass to accelerate. Sometimes that's a centripetal acceleration, or looking at the force of gravity, the universal gravity formula. Other big ideas that are awesome to hit on are conservation of energy and conservation of momentum. So we're going to look at conservation of energy to determine the speed of the center of mass of any rolling object, but a hoop when it reaches the bottom. And we've got something that starts at the top and ends at the bottom. Often we'll just say that the kinetic at the top equals the potential at the bottom. So conservation of energy generally is EO equals EF. In this case, EO would be at the top, and it would be at the bottom of the ramp. So that's conservation of energy. That no work is done in our system, so we can say the total energy of the system stays the same. For the case of our hoop rolling down the ramp, and this comes from this page in the AP Physics 1 workbook, we have a torque being exerted from the force of friction causing the hoop to roll, and that means that the total gravitational potential energy it had at the start equals, or is divided up into, the two buckets of rotational kinetic energy and what's called translational or linear kinetic energy. So we've got to maintain this conservation of energy, and I'm going to work this a little different than I did in class. So at the top we've got our gravitational potential energy. At the bottom we have our linear kinetic energy plus our rotational kinetic energy. And then we're just going to substitute in for each of those. So our gravitational potential energy is mg delta y, and our linear kinetic energy is 1/2 mv squared. These are all from the reference table. And our rotational kinetic energy is 1/2 I omega squared. And let's just remind ourselves, we're looking for the linear speed of the center of mass as it rolls down the ramp. So this omega isn't something that was given in the problem, the angular velocity, but we know we can express the angular velocity as the linear velocity of the center of mass divided by the radius. So I'll just use a little r here. So I'm going to keep going. We'll plug in. So mg delta y equals 1/2 mv squared plus 1/2 I times v over r. And then that's squared. So I'm just going to put the squareds on right now while I'm plugging in for v over r so I don't forget the squared. And that's a common mistake. So another way that we can simplify this is we can look at I. So I is generally described as some coefficient. So I for the hoop mr squared. I for a disk is 1/2 mr squared. I for a sphere, a solid sphere, is 2/5 mr squared. So the general form of the moment of inertia or rotational inertia is a coefficient times mr squared. So I'm going to call this coefficient A. A is the coefficient for this number, this fraction, before mr squared for the moment of inertia. And you'll kind of see why I do this and how it makes a difference as we go along. So trust the process. So we'll pick up where we left off. So mg delta y equals 1/2 mv squared plus 1/2, and we'll call it A mr squared. I'm sticking with the little m's and r's, which I used before, times that v squared over r squared. I'm just going to highlight this to make sure it works. The only thing I changed from here to here was I replaced the moment of inertia with A times mr squared. So now that we have this written out, we can see a couple things. So first off, in this term we have 1/2 times A times m times r squared times v squared divided by r squared. So we've got an r squared divided by r squared, and that would give us 1, a factor of 1. So then another thing that I notice is we have a m in every term, and you need to have whatever's going on in every term, or whatever operation you do to side of an equation that has one term plus another term, you have to do to every term. So we're going to divide all these terms by m, and then the m's cancel and become 1. So what do we have left? So we have g times the height, or the change in height that this rolling object experienced, equals 1/2 v squared plus 1/2 times A times v squared. So we can pull out the 1/2 and pull out the v squared, or isolate them, as I've heard some of my students use that term. So 1/2 v squared times, so how many times does 1/2 v squared go into 1/2 v squared? 1. And then how many times does 1/2 v squared go into 1/2 A times v squared? A. And we have g delta y. So then we're going to multiply both sides by 2. We probably could have done that step up here as well, remembering that we needed to do it to every term. So we're going to multiply both sides by 2. So we end up with 2g delta y equals, so that 2 here and 2 here cancel, and or become 1. So we have v squared times 1 plus a. So generally speaking, for any, so then we would just divide by the 1 plus a and take the square root. So for any object that is rolling, for a rolling object, we can find it as the square root of 2 times g times the change in height divided by 1 plus a, where a is the coefficient in front of the moment of inertia. So for a hoop, that coefficient, so the I of the hoop was just mr squared, so that coefficient was just 1. So it would be the square root of 2 times g times the change in height over 1 plus 1, which is 2. So it's just the square hoop, but for a sphere, it would be the square root of 2 times g times delta y divided by 1 plus 2 fifths. So that would be, this is 7 fifths. So that would be the square root of basically the 5 on top, so 10 g delta y over 7. Now you don't need to simplify in the way that I did, and there's never been a point on the rubric for simplifying improper fractions or anything like that. So if you're feeling tight on time, just kind of move on. You don't need to simplify. But I wanted to give students the ability to see how the speed for an object that is rolling at the bottom of a ramp with a height y is impacted by the moment of inertia. So it is impacted by the moment of inertia, but notice that the mass doesn't matter, not in this equation. And the radius of the object doesn't matter. Using the capital R's to stand for it's an object, so it has a fixed radius, not a variable r. But A does. A does. So this is, or I does. A is this coefficient in front of the moment of inertia. That sounds helpful. Let me know what you think.